So the principle of amplification and biasing, we will do a formal approach to biasing, um, because in many textbooks about electronics, you see the design of the signal processing, let's say the biasing mixed up through each other, and we want to separate. What we want is an amplifier that processes information in the best possible way, and the biasing is the condition that we have to apply that this will happen. So let's not mix it up and take a clear separation between the concept of biasing and the signal processing that should be done by the amplifier. So let's start at the beginning. What we have is a source, a load, and what we want is an amplifier. In this case, I used a resistive source and a resistive load, but this is not necessarily important. It can be any type of complex impedance there, but for the sake of simplicity, today I will just only confine myself to resistive source and load. So we have a source providing a voltage and a current, and a load that needs to be driven with a voltage or a current. So what is an amplifier? What do we want from this amplifier? Well, we want signal values at the load to have a unique correspondence with those of the source. If so, if this is the case, then we can retrieve the information from the source. It doesn't need to be without distortion, as long as we can retrieve the information. That's important. But of course, in many situations, it's just better to say, well, you want to have a load signal that is a copy of the source signal with a larger available power gain. And that is the second issue. Available power gain, available power at the output of the amplifier must exceed the available power of the source. For those who do not know what available power is, please go to the book or go to the homologation program, because there it has been done. But the words are quite clear. Available power is what a source has available, and the available power of an amplifier is what the amplifier has available at its output. So let's do it. Let's put our amplifier there, because everyone tells you that transistors are active devices. So let's just put one there. We put a transistor there, and we connect the input the terminal of the device to the source and the output terminal of the load. And here in this case, we have one common terminal for source and load, an amplifier. And of course, you know, nothing is going to happen, but let's be clear about it. Why does nothing happen? Well, you know the device equations maybe for a FET. So, and we know that the currents can be written as a function of the voltage. And if there is no voltage, there's no current. It's passive. The characteristic pass through the origin. If you put nothing at the input, and the input is both VDS and VGS, if you don't know, put no voltages there, then there are no currents. That is what happens. So the transistor is a passive device. We only have drain current if there is a non-zero drain source voltage and the gate source voltage exceeds the threshold voltage. Since we here have, well, we have nothing. Well, maybe if the signal is large enough, we have something at the input, but we have nothing at the output. So the operating points are all zero, and there is no, you can put your oscilloscope at the output, but probably you have a little bit crosstalk, but for the rest, you will measure nothing. So we have no load signal, and we need to do something about it. We can add a battery to the output. And I will put the battery in an inconvenient place, but it's nice for the story. I put it there. And now I have my battery there. So now I have a VDS not longer zero, because there is a DC path and the drain current is now positive. But as long as the gate source voltage is still too low, nothing happens. So the load signal is only there if the source voltage exceeds the threshold, which means there is no unique correspondence between source and load signal values, because many signal values, let's say almost all signal values, will correspond with load signal value zero. So that's not a unique relation, I would say. Unique correspondence. So what we do is also put something at the input. Something that there is always current. Under all signal conditions, there will now be current. We just add this threshold, maybe a little bit more, and then there will be currents flowing, IDS through the device, drain source, and IGS at the input. And of course, for FETs, this DC, this operating current IGS is usually assumed to be zero. It's a little bit leakage current of a few picoamps maybe, but for bipolar transistors, it can be still there. And this model is also valid for vacuum tubes, for junction FETs, for bipolar transistors, for everything that they will probably invent in the future with 3 wires and that has amplifying capabilities. That makes it so nice to use this concept. So we have a load signal for all values of the source signal if the sources, of course, also VDS are large enough. And then we have a unique correspondence. So now we have an amplifier, but the only problem is that through our load and our source, we have this DC currents. We have IDS flowing and IDS flowing. And now your load and your source is resistive, so maybe it can carry those currents, but it's not what we want. We want to have maybe a capacitive load or a capacitive source, and then it does not have this DC current path. So what we then do is we add the bias currents. We add them here and we add them there. And if you do that, then nothing flows through the source and through the load. And we just have our biased amplifier stage. So no bias currents through the source and the load, and all these characteristics from source voltage to load voltage, from source voltage to load current, from source current to load voltage, and from source current to load current, all these characteristics now pass through the origin. So for very small signals, you could say you can linearize the characteristics in this new origin. That's another way of describing it. And then calculating all these transfer parameters of the stage itself and model it with a 2-port as we will do later. So this is now our biased amplifier stage. And I must admit, it's not very practical, but this is for the next part of our lecture to make it practical. But first we need to have a concept that clearly makes a distinction between signal and biasing, and that is what we are doing here. So you could remove now the source and the load, and you have your biased amplifier stage. And if you remove it, nothing happens because there was no DC current flowing through the source and no DC current flowing through the load. So there was 0 voltage across both. So nothing happens. This transistor is still perfectly biased. Only it is very impractical. And why? If the temperature changes, well, then you need other sources, other VGS and other IGS to obtain the same values at the output. And if you put another device in it and there are device tolerances, then you also need other sources. But this is a topic I would like to discuss later, how we do this, how we can use error reduction techniques to improve it, and how we convert this concept into a practical circuit. In this configuration, you see that no current is flowing through VGS and no current is flowing through VDS, so there is no power delivered by those 2 bias sources. But the voltage across IGS has the positive at the top node. So the positive voltage is here and the negative voltage is here. So the positive current direction will be from positive to negative. But the current flows from negative to positive, which makes the product of current and voltage, branch current and branch voltage, negative, which means this device is delivering power. That's the definition of an active device. The definition of an active device is that it delivers power, so the product of voltage and current is negative. And this is also the case for the output IDS. You can see it, there's a positive voltage across it, but the current direction is opposite. It's not flowing from plus to minus through the device, it's through the external circuit. And it's flowing from plus to minus through the external circuit, so from minus to plus in the device, which makes it an active source. So that are the 2 batteries. Now you can also do the other way around. Then we have no voltage across IGS and IDS, which makes them passive element. Nothing happens. There's no dissipation at all, and there's only current flowing, and there's no dissipation. And there is power delivered now by VDS and VGS, because the current through VGS is flowing from the minus terminal to the plus terminal internally, which makes the product of current and voltage negative, which makes it a energy source, a power source, instead of a dissipating element. And the same you could say for VDS. Of course, IDS in practice will be very small, but this has nothing to do with the concept. It's just the numbers. Yes, maybe we can ignore things, but that's something else. It has nothing to do with the concept. So here's the power is delivered by VGS and VDS. And as I told you, we have now all characteristics through the origin, and you could measure of this. You could consider this, well, for very small excursions, you could say, well, let's model it as a linear two-port. So we are going to linearize it in the operating point. And now we have there an active two-port. Yes, but there are 4 batteries in it and a transistor. But we don't worry about it anymore. We just replace it with controlled sources, as we have done in the bachelor course where we discussed these 2 ports. And that's why we usually speak of active devices, because we use models like this for them. But remember, the transistor itself is a passive device, but the whole constellation, the whole structure with the bias sources around it makes it an active one. So we know also from the bachelor course that the maximum available power gain of a unilateral linear resistive 2-port is 1/4 A times D, which is 1/4 the current gain times the voltage gain factor. The current gain factor times the voltage gain factor, and 1/4. And that is the maximum available power gain if this thing is unilateral, which means if a change at the output is not observed at the input. So there's only one direction, as the arrow tells you, there's only one direction of signal transfer from input to output. Well, that is the story about the fundamental of biasing and amplification.